In the last lecture, we discussed about Reynolds transport theorem, which related the mass conservation and momentum conservation, or what we derived it for any general variable which we called n. We could relate the control volume formulation with the system formulation, whereas the system is a entity which is a control mass, that is a fixed quantity of mass, whereas in fluid mechanics or in this course we are generally dealing with a control volume approach, where we have a control volume, a fixed region in space or a specified region in space through which the mass can come in and go out. So, the conservation equations, the mass conservation and momentum conservation, energy conservation or angular momentum conservation, all those conservation equations we know in terms of or for a system from rigid body dynamics. So, what we are doing in this week or in this module is we learnt first that for a general variable n or an extensive property n and the corresponding intensive property eta, we derived the Reynolds transport theorem, that how we can convert a derivative in the system form, because all the equations we have dn by dt kind of term. So, how we can write that dn by dt in the system formulation, how can we convert into control volume formulation, and now we are going to apply this in this lecture for mass conservation, and then we will look some examples. So, let us recall the equation that we derived. The equation states, the Reynolds transport equation, that the rate of change of a extensive property n is equal to rate of change of the property in the control volume. So, subscript CV refers to n in the control volume, and then plus integral over Cs, which is control surface, eta rho v dot dA. So, eta is the corresponding intensive property, which is n divided by mass or n per unit mass. So, couple of things, that we have this plus sign because we assume or we have derived it that the velocity is outward. If velocity is inward, then this sign will become negative, and this velocity v is measured relative to the control volume. Okay. So, let us try to apply this to derive the mass conservation equation. So, when we want to derive mass conservation equation, we will consider that n is equal to m or mass, and correspondingly eta will become m over m. So, which gives us 1. So, eta is 1 and n is equal to capital M, and let us substitute it here. So, n is replaced by m. So, dm by dt, or rate of change of mass in the system, that will be equal to del by del t m c v. So, in place of n we have now replaced with m, that is equal to integral over control surface, eta is equal to 1. So, it becomes rho v dot dA. And we know that the mass conservation equation basically refers to that the mass in the system remains constant. So, that means the rate of change of mass in the system is 0. So, if we substitute that the value that we obtained or the expression that we obtained for dm by dt in this equation, then we will get the mass conservation equation, that dm by dt of our system is equal to 0. So, that is mass conservation equation, which simply states this. This is del by del t of m in the control volume, written in terms of rho and v. So, if rho is varying in the control volume, then we can put an integral. So, del by del t integral over the control volume rho and integrated over V. So, remember here this V, a horizontal line cut, this is the symbol that we are using for volume, because we have another V here which is V vector, and this is velocity. So, plus integral over the control surface, which is the boundary of the control volume, integral over rho V dot dA, that will be equal to 0. So, this the first term is rate of change of mass. So, rate of change of mass within control volume rho dV will be when you integrate over the control volume, this will give us the mass in the control volume, and its derivative with respect to time will be the rate of change of mass within control volume. And the second term gives us the net rate of mass flux or outflow through the control volume. Okay, so, the net rate of mass outflow, that is what we call the flow or the mass flow that is going out of the control volume, is given by this term. Now, we can call this also as continuity equation. So, mass conservation equation is also known as continuity equation. We can write this taking this term on the other side. So, if we want to say that net rate of mass inflow, so then we can say the rate of change of mass within control volume is equal to net rate of mass inflow. So, the negative sign represents that the mass is coming in. So, that is pretty obvious when you think that in a box, the mass that will be present at any time, that will be equal to mass coming in minus mass going out if there is no accumulation. If there is an accumulation, so the accumulation is equal to mass coming in minus mass going out. Okay. If we write that both the terms on one side, then we can say that the rate of increase in the control volume plus going out. So, that will be equal to the net rate that is coming in. Okay. So, this equation is pretty simple to understand. Now, if we consider a special case that if the flow is incompressible, so we can treat rho as constant. So, if the flow and the fluid is incompressible, then we can treat rho as a constant. If rho is constant, then we can take rho out of the integral sign in these places. So, rho integral over the control volume or del by del t. So, that is basically the rate of change of control volume plus rho integral over the control surface area integral V dot dA. Now, if the control volume does not deform, so if the volume in the control volume of the control volume does not change, if it is a rigid volume, then del by del t of control volume will be 0 if shape and size is fixed. So, then we can write del by del t over the control volume is equal to 0. So, then you end up with only one term on the left hand side. So, integral over the control surface V dot dA is equal to 0, and if the flow is uniform at the boundaries. So, if over the entire control surface or wherever the flow is coming in or going out, if the velocity is same on an inlet or an outlet, then in place of integral you can simply write this in terms of summations, that summation over all the boundaries V dot dA. Okay. So, we need to apply these equations depending on the case we have at hand. Now, if we look at if the flow is steady, it is compressible. So, if the flow is steady, that means the density does not change with time, but it may be a function of a space. So, rho is a function of rho x y z. Then we have the mass conservation equation, and because the flow is steady and if the control volume is fixed, then we can have this term is equal to 0. So, you will have integral over the control surface rho v dot dA is equal to 0. Okay. Or if the velocities are uniform at the inlet and outlet boundaries, then integral you can turn it into summations. So, integral or summation over rho v dot dA is equal to 0. So, summation means you can have one boundary, two boundary or three boundaries. You can write sigma over 1 rho v dot dA plus sigma plus rho 1 rho v 2 dot a 2 and so on, and sum it over to get the answer. Okay. So, let us look at an example. So, this example states that blood enters in the mother tube at a flow rate, you have been given the flow rate, and this mother vessel is bifurcated into two daughter tubes, and the blood leaves the first daughter tube. So, let us look at the figure. The blood enters at this point, and then this artery you can say, or a blood vessel, it is bifurcated into two. So, this is what is being referred to mother tube or mother vessel, and then it has two daughter vessels. So, what daughter vessel 1, daughter vessel 2. The diameter of the daughter vessels are given, as well as what you have been given is the flow rate at which it enters. So, 1 centimeter cube per second. The diameters are also in centimeter, and then it says the blood leaves first daughter tube at an average velocity of 1 centimeter per second. So, the velocity here is 1 centimeter per second. Now, what we need to find out is the average velocity at this section. So, V at this at section 3 is what is to be found. You can assume the flow to be steady and incompressible. So, we start with the mass conservation equation, and in this mass conservation equation, because the flow is steady, so we can take this out. The velocity is given is average velocity. So, we can write, and then rho is a constant. So, we can take rho out, and the equation will be integral over the control surface rho v dot dA is equal to 0. We can divide by rho. So, we have integral over the control surface v dot dA is equal to 0. We can take a control volume or we can have the, so we can draw a control volume which is following the just outside the vessels, and this surface will be a control surface. Now, the flow is coming in at three sections: section 1, section 2 and section 3. So, the flow is coming in or going out at these sections, everywhere else the flow is 0. So, when we apply this equation integral over control surface, we will have 3 surfaces. So, integral over control surface 1, which is the section at 1 where the flow is coming in, V dot dA plus V dot dA at section 2, the exit of daughter vessel 1, and integral V dot dA, the exit of daughter vessel 2, section 3. Okay. So, V dot dA, the flow is coming in and the area vector is pointing out. So, V is pointing inward, whereas A is pointing outward. So, you will get V dot dA with a minus sign. So, you will have minus, and V dot dA is basically the volumetric flow rate at section 1, the value we know. So, Q1 is equal to 1 centimeter cube per second. We write this in terms of letters. So, Q1. Now, section 2 V dot dA, the flow is going out. So, the velocity is outward, the area normal will also be pointing outward at this surface. So, V dot dA will be positive, the area will be pi by 4 d1 squared, and the velocity, mean velocity there is V1, which is equal to 1 centimeter per second. So, we know V1, we know Q1, we know D1. At section 3, again the flow, we assume at least that the flow is going out. So, if the flow is going out, then the area normal and the velocity vector, they point in the same direction and the sign is positive. Area is pi by 4 d2 squared into V2. V2 is the velocity, that is the mean velocity at the exit of daughter tube 2. So, let us substitute the values in, because all the numbers are in terms of centimeters. So, centimeter per second or centimeter cube per second. So, we can use the same units. Q is equal to minus 1 plus pi by 4, 0.8 centimeter is d1. So, 0.8 squared, V1 is 1 centimeter per second. We also know d2, pi by 4.6 squared into V2. So, when we solve it, we can obtain the value of V2, which will come out to be 1.76 centimeter per second. So, I suggest that you verify this value and check for yourself if this is correct or not. Okay. So, this is a simple example, and you could have just used A1 V1 is equal to A2 V2, or A1 V1 is equal to A2 V2 plus A3 V3 to find this out. So, that will come out when you use this. Basically, this is flow rate or volumetric flow rate, that is equal to the exit, the flow coming out from these two daughter tubes A1 V1 plus A2 V2, that is equal to the total flow that is coming in. Now, suppose if this velocity, the numbers would have been such that you get V2 is equal to negative. So, that simply means that the flow is coming in from the tube 3 rather than it is going out. Okay. So, let us look at a next problem. So, it talks that there is a plane which is drawn here, and the velocity field is given by a vector v x I plus y j. So, this is the velocity vector, and it asks us to evaluate the volumetric flow rate. So, volumetric flow rate is nothing but the integral over the area of this plane v dot dA. Now, we already have vector v in such case, or in this case, what we need to find is the area vector dA first. So, to find volumetric flow rate, we need to calculate dA. So, if we take a small area on this plane, you can see that this plane we can take a small area which has dimensions dl and dy. Now, this can be projected, if you project this area on the two planes, you can project it on yz plane and you can have a projection on xy plane. So, on the yz plane, if you project it, then the dimensions will become dz. So, dl, basically the projection of dl on the yz plane will be dz. So, the area, the projection will be dz dy on the yz plane. On the xz plane, xy plane, the projection of dl will be dx. So, you will get on the xy plane dx dy will be the length of this small area, where dx is the projection of dl on xy plane. So, we can write this area vector dA in terms of dy dz, which is the projection on an x plane, means the on x plane means the yz plane and its normal points in the x direction. So, dy dz I plus dx dy k. On the xy plane, the normal to it, the normal vector to will be along the z direction. So, unit vector k. So, we can write dA is equal to dy dz I plus dx dy k. Now, we know the area vector dA. So, let us substitute v dot dA. The other thing we will need is because we have taken an elemental area and its normal vector, but we will also need to relate when we integrate this, then we will need to relate x, y and z. So, we need the equation of this plane. So, if we write down equation of plane, because this the plane that has this intersects x, y, z planes at, let us say, if the intercepts are a, b and c, we can write the equation of plane is equal to x by a plus y by b plus z by c is equal to 1, where a, b and c are the intercepts on x, y and z axis respectively. So, if we look at this plane at x axis, it intersects at this point where the intercept is 4 meter. So, x by 4, y axis it is parallel to y axis. So, it never intercepts it. So, that you can say intercept is at infinity. So, that term becomes 0, y by b, b is infinity. So, y by b will become 0 and then you have the intercept at z axis at this point. So, c is 3. So, x by 4 plus z by 3 is equal to 1 is the equation of this plane. Now, we can write down or substitute the values integral v dot dA. So, we can write in place of v x I plus y j dot the area vector dy dz I plus dx dy k. Now, if we look at when we take dot product, I dot I is 1, I dot k because they are normal to each other. So, that will be 0, j dot I normal to each other. So, that product will be 0, j dot k the product will be 0. So, we will have only one term where we have I dot I. So, that means this term and this term the product of these terms you will have inside the area. So, x dy dz I dot I is 1 and integral over the area. So, if we look at these over the plane, then the limits go from y is equal to 0 to y is equal to 5, okay, and the other limit for z from z is equal to 0 to z is equal to 3, because we have x dy dz. Now, we know that x in terms of z can be written from the equation of this plane. So, we can substitute that. So, let us write this. We can write x is equal to 1 minus z by 3 multiplied by 4. So, x by 4 is equal to 1 minus z by 3 and x is equal to 4 into 1 minus z by 3. So, we can substitute this here and we will get integral z is equal to 0 to z is equal to 3. X is not a function of y. So, we can integrate with respect to y straight away and we will get y, which will be 5 minus 0 if you put the limit. So, we will get this 5 x. So, in place of x we can write 4 into 1 minus z by 3 dz. Okay. So, when we simplify it, 5 into 4 is 20. So, we will have 20 integral 0 to 3 1 minus z by 3 dz. Okay. Let us integrate it. So, that will be equal to 20 within bracket. When you integrate 1, you will get z minus z when you integrate. So, z square by 2 and 1 by 3. So, z squared by 6 integral the limits from 0 to 3. So, 20 into when you substitute the limits. When you put z is equal to 3, that becomes 3 minus z square by 6. So, 3 square by 6, that means 9 by 6 and minus 0. So, 3 minus 9 by 6, which is basically 3 by 2. So, 3 minus 3 by 2, 20 into 3 by 2 or 1 by half times of 20, which is 30, and the unit will be we have not been given unit here. So, yeah, we have been given the units in terms of meters and let us say that x and y in these are in meters and the velocity is in meters per second. So, if that is the case, then the answer comes out to be 30 meter cube per second. Okay. So, we can write the units here also, 30 meters cubes per second. So, so what we need to look at here is when you have been given such a plane, the effort goes into finding out the unit normal vector, and if we need to relate the x and y in such cases, then we need to do that a bit of vector algebra or a bit of geometry where we need to find the plane equations, etc. Okay. So, let us look at another example. We have already discussed what is a boundary layer. Boundary layer is the layer near the wall in which the viscous effects are important. So, when you have flow over a flat plate, as has been shown here, when the flow enters, the uniform flow enters over this plate, and because of the no slip boundary condition at this wall, the velocity at the wall will become 0 and there will be gradient in velocity inside the boundary layer. As you go above boundary layer, the velocity becomes uniform. So, it has uniform velocity. Of course, when this change is happening in the velocity profile, because the velocity here and here is same, there will be some mass that has to go out of this control volume. So, a control volume A, B, C, D has been drawn here, and what we need to find is the mass that is going through. Calculate mass flow rate across surface B C of control volume M A, B, C, D. So, let us say what we need to find is M dot B C. Now, the velocity profile, because this is at the section A B, velocity profile is uniform, or the velocity is same across all from 0 to y, whatever y we take, whereas at section C D we see a change in velocity. So, this velocity has been given as a function of u by capital U is equal to 2 y by delta minus y by delta squared, where delta is at any location, delta is the thickness of boundary layer. At point D, this thickness has been told that this thickness of boundary layer at point D is delta D. What we see here is two dimensional picture, and the plate width which is normal to this normal to the board is W. So, the area of the plate if we take, then the length multiplied by the width. Okay. So, let us apply mass conservation equation here. We write down the mass conservation equation in the form that we have just derived. So, del by del T over control integral over the control volume rho dV plus integral over the control surface, or the area integral rho V dot dA is equal to 0. Now, the flow is we can assume the flow to be steady, and we can assume the flow to be incompressible. So, density is constant, flow is steady. So, we can take So, we can take rho is constant and the first term becomes 0. Okay. So, we end up with this simplified equation rho V dot dA is equal to 0 integrated over the control surface. We can take rho out of the integral because the flow is incompressible. Now, what we can do for this control volume A, B, C, D, we can expand and write down the flows or the V dot dA term over each part of this control surface. So, let us look at AB first. So, if we look at AB, the flow is coming in and the area vector will be pointing outward. So, the first term will be negative because the flow is coming in, V and dA they are in opposite direction, and so this term will give you rho multiplied by u. U is the velocity and the area will be W into delta D. Okay. So, the area through which the flow enters is delta D and W, which is the width normal to the board. Okay. Now, let us look at BC. So, VC is the surface on which we need to find mass flow rate. So, V dot dA is the volumetric flow rate. So, we can say that this is the mass flow rate through BC, and this is what we need to find. Let us look at the third surface CD. So, the flow is going out, that is the velocity direction, and the area vector will also be pointing outward. So, we will have rho, you can take rho outside or inside. So, rho and velocity. So, velocity is u by u we had been given. So, we have written this small u in terms of capital U into 2 y by delta. At this particular location delta is equal to delta d. So, we have written 2 y by delta d minus y by delta d squared into w into dy. Okay. Because the velocity profile is varying with the distance from 0 to y. So, we will integrate it from 0 to y. Now, the last surface dA, because this is wall and this is non-porous. So, the flow from this wall will be 0. So, we have neglected this term. Now, we need to find out m dot. So, basically what we need to do is integrate from 0 to y and then rearrange the terms to find m dot. So, we take this term on the left hand side which is basically m dot b c, that is equal to, we take this term on the right hand side, the first term. So, this will be positive rho u w delta d, and the second term or the term under the integration which is mass flow rate at section C D, this will become negative minus, and we can substitute the limits for y. So, y is equal to 0 to delta d rho w u, all three of these are constant, within bracket 2 y by delta d minus y by delta d squared into dy. So, we can simplify this, and when we simplify we will get rho u w delta d minus rho u w, and let us integrate. So, when we integrate we will get 2 by delta d into y squared by 2. So, we will get 2 by delta d, both of them are constant, and 2 y squared by 2 and 2 will cancel out, minus 1 by delta d squared, which is constant with respect to y, because delta d is varying with respect to x, and when we integrate y squared we will get y cube over 3, and we can substitute the limits from 0 to delta d. Okay. So, that will be equal to rho u w delta d into, so y squared that will become delta d squared by delta d. So, you will have delta d minus, substitute delta d in place of y. So, delta d cube divided by delta d squared and divided by 3. So, you will have delta d by 3, and when you substitute the limit as 0, because of that the terms will become 0. Okay. So, you have this rho u w delta d minus this multiplied by rho u w. So, if you look at what you get, this rho u w delta d minus 2 delta d by 3 rho u w. So, rho u w delta d minus 2 delta d by 3, and if you solve, what you get, the final answer, delta d minus 2 delta d by 3 is delta d by 3. So, you will get rho u w delta d by 3. Okay. So, that is your final answer. Now, just sorry, this has overlapped. So, what you can see is how will the problem change if the plate is porous. So, if the plate at AD is porous, you can think of because the flow rate at the surface AD will not be 0. So, you will need to take into account the flow rate at surface AD also. Okay. Another example where we are looking at gas flow from a tank in chemical engineering applications as well as in medical applications, you often have a gas tank and from which the flow is coming out or going in. So, if you look at this, a tank of volume V and this has compressed air is in it. A valve is there at the tank and this valve is opened and the air starts escaping. The mass flow rate of the air escaping is equal to rho into C, where rho is the air density in the tank and C is a constant. They suggest that the initial density when the valve is opened, the density in the tank is rho naught. So, what we need to do is develop an expression to find out the density change with respect to time, because when the gas escapes from it, the density which is, if you take ideal gas law, if you assume the gas to be ideal, rho is equal to P m by R T, right. So, the density, the pressure is going to change and because of that the density will change. Okay. So, then the next part is that you need to find the time required in which the tank density will drop to half its initial value. Okay. So, let us write down the conservation equation. Now, the density is not constant with respect to time. So, this term will be non-zero now, okay. And there is only one control surface through which the gas goes out. Okay. So, the density is not constant with respect to time, it is changing with respect to time, but we can assume the density inside the cylinder to be uniform. So, over the volume, when you integrate over the control volume, rho is constant. So, we can get rho out of the integral. So, del rho over del t, and when you do integral dV, you will get the volume. So, V del rho over del t, this is the first term, and the flow is going out. So, this will be positive. And if we write down in terms of mass flow rate, because we have been given mass flow rate. So, V dot dA is flow rate or volumetric flow rate multiplied by density. So, what we have is mass flow rate. So, this term becomes m dot. So, we can write V del rho over del t plus m dot, this is the equation. Now, we can substitute m dot is equal to rho into C and take it other side. So, what we could do is write V del rho over del t plus C into rho is equal to 0, or del rho over del t is equal to minus rho C over V. Okay. So, that is the expression for rate of change of density with respect to time. Now, we can integrate this equation and we will get this final expression. So, let us integrate it. We reshuffle it and we get del rho over rho is equal to minus C by V del t, and we integrate say initial density at time t is equal to 0, rho is equal to rho 0, and then at time t it becomes rho. So, when you integrate, you will get ln and you substitute limit ln rho. So, ln rho minus rho 0, or ln rho minus ln rho 0, which you can write ln rho over rho 0. This is equal to minus C over volume of the tank into T or T minus 0. So, when you write this in the exponential form, you are going to get this. Now, you can find out the time that will be required for it to become 50% by substituting that rho is equal to rho naught by 2. So, you can write that rho by rho naught is equal to half. So, ln 1 by 2 is equal to minus C over V t, or we can find ln half is equal to minus ln 2. So, we can write t is equal to V ln 2 over C. That will be the time required for the tank density to drop to half of its initial value. Okay. Sorry, so this has gone inside. I will just leave it that. Okay. So, what we have discussed today is we applied the Reynolds transport theorem to derive a mass conservation equation, and then we have looked at 4 different problems that how we can apply the mass conservation principle or the macroscopic mass balance to solve problems and find the mass flow rates, etc. Okay, so we will stop here. Thank you.